Where's my gong or something?
Boom.
Huh?
Can we get one?
Well,
The real
usually
one?
he's got. Well, you maybe missed those classes. Sometimes there's sound effects.
Oh, okay.
It's like,
We should
oh.
have just stolen the gong from Battle Hack.
All right. So, quiz question: what can we accomplish with a let expression that we could not accomplish otherwise? What was the answer I was looking for there? Good.
Essentially making variables, like, or at least assigning values to essentially name variables. So creating a short-term variable environment.
Okay. So creating variables, important. Temporary environment. So creating variables temporarily available and executing an expression within that temporary environment. Fair enough. So another way of giving us local variables. That may be a short way of saying this, local variables in our language. Okay. All right, so homework assignment was to add a let expression to your code, right? And did we start that last time? Like, did we add it to our?
We added it to parse EXP, but nothing else.
So, yeah, here's our let. Let takes in a list of name value pairs, and then the body, right? So that's what a let expression looks like. And then are we converting it now? A let expression is a list. So it's this guy. It's an app expression whose car is the list let expression. So that's a placeholder. Whose catter is an app expression that is a list of app expressions in terms of how it's being parsed currently. And then whose body is an actual app expression, or whose body is some expression, right? But these guys would definitely, this would always be an app expression. That correct? All right, so a let always is an app expression. Therefore, inside of our eval expression, we're going to be updating our thing for a let expression. So last time we updated for an if expression. So now we have an op, a boolean arith op expression, an if expression. So now we're going to do a similar thing here. So let's copy this, paste it here, and say this is a let expression. So the first element of the app expression is a let expression in this case. So we're asking this question right here, and we want to change this to let. All right, so if bucket 0 of bucket 1, which should be that guy right there, if that guy is equal to let expression, then do this crap. So we need to maybe eval let expression.
I think wouldn't it be better if we just did eval expression?
Possibly. Yeah, so just let's get it updated so it doesn't say if. We'll get an error. Anyways, so what's the body? Let's figure out what the body of this guy is. The body of this guy is, so we already peeled off the car. This is the car of the cooter. This is the car of the cooter. And then this is the car of the cooter. Okay. You don't want to say cooter? CADDDR? That's not a thing?
Sounds interesting.
You just let it up.
Well, that's upsetting. All right, so then you want to say a val expression. List ref of LCE3. Okay, so this gives us the body of that guy. But we're not evaluating it in this environment. We need to evaluate it inside of an extended environment, right? An environment that is extended with all of these name value pairs. All right, so I would suggest you write an extend env for let. Fair enough? All right, so let's go up here. We're going to write it here first, just so we... So we're going to create the environment we want to evaluate this guy in is the extend env for let. Passing it, let's go ahead and give it this list of app expressions here.
You're giving me the list of expressions. I did it a little differently. I called it extend env for lambda within, like that's what I had a question about, was do we need to call it extend env for lambda? Because either or, we can just extend the environment passing it the list of bars and bells and then the environment. So we just change that so it's more universal.
Sure. But right now, extend env for lambda, doesn't he take in a list of variable names and then a list of corresponding values?
Yeah, so what I did was I extended let environment. I called that and passed extend env for lambda, mapping the get low bars of app expression and get low bells of app expression.
Okay. Did we write that already?
No.
Let's see what we got up here. We have...
No, I created two helper functions.
Yeah.
So that we have a get low bar and get low bell.
You can just do it recursively. It makes no difference.
Well, bottom line is we need to extract. I guess in my mind, it doesn't necessarily, there's not an efficiency difference. I'd rather say let's extend something for a let, have it take in the format that we're currently having it take in for a let, and then we are going to piece that out into its stuff, right? But I mean, at the end of the day, we're going to end up doing the same thing. We're using our constructors for extending our environment, giving us a new scope, all that jazz. So I would suggest then that what we do down here is we want to extend env for let, passing it this guy. So this is our list of, let's see, do we just have, what did this guy start off looking like? All right, so this is our list. So we want to pass it that guy. The list that contains all of our name value pairs, essentially, it's going to come in there as an app expression currently, even though they're technically not app expressions, but that's how we're currently parsing it. So we're going to go ahead and take in that. So this is list ref 0, list ref 1, list ref 2. Is that our list of variable value pairs is list ref 2? That sound right? All right, so we're going to pass in list ref LCE2 along with the current environment. All right, so we're going to, assuming we're looking at a let expression, let's evaluate that expression. Here's the body, so evaluate this expression, the body of the let, in the environment extended specifically for lets, which takes in the list of name value pairs, as well as the existing environment, and then that guy will magically create a brand new environment that is the locally extended environment. Okay? So this code here should already be right now. As long as we get extend env for let working, we should be good to go. All right, so let's go up here and write that guy. All right, didn't I start writing it? Extend env. Did I not start writing it yet? No, I thought I had. Extend env for let. This guy's going to take in a lambda, and he's going to take in, as it stands right now, a an app expression. So the thing he takes in right now is an app expression. So we're going to go ahead and we're going to remind ourselves of that. We'll say he takes in an app expression as well as an existing environment. And then he's going to do the extend thing. All right. So first thing we need to do is we need to get this guy pieced out into, I guess, into his pieces. Now, we can leverage extend env for lambda here, which, you know, is kind of what you want to do, as long as we can turn this into low vars, low vals, right? And this is our helper, so this is, that guy's not going to do us any good. That's something unrelated. All right, so really what we need to do is if we can turn this app expression into a list of variable names and a list of values, we can call extend env for lambda and have it do its thing, right? Is that right?
Yeah.
Extend env. Yeah, we have the empty. Okay. So we are looking at something that looks like this. So for right, well, we're looking at something that looks like that. And I want to create something that looks like the list AB and then the list 5-7. That's what I need to get out of there. How am I going to do that? Go ahead.
What I did was I passed in to a helper function, or I just passed it in, but the cooter of that, so it's a list containing both of those. And then I created two other helper functions that were get low var and get low val, and I mapped those across each element in that.
Okay. So the first thing you're going to do is you're going to go ahead and you want to kind of extract the list of these two lists.
Yeah.
So move past, so get the cooter of this, which is the list of these guys, right off the bat. So we'll kind of rip the app expression off. So we're left with just two lists. Okay. Then the first two lists is a name value pair. The second two lists is a name value pair. So really what we have is a list of name value pairs. So right off the bat, if we just say this, cooter app expression, this guy just turned into a list of name value pairs. That's what we got right there. Okay, so now I have something that looks like that. It's a list containing those two things, followed by.
Please look at the app expression on top of that.
Oh yeah, we have this. We have these two lists. That looks just like that, right? All right, so we have that guy. So now we need to build from that the list AB and the list 5-7. How do I extract just the AB from that?
I mapped, well, that function, what it did was it took the list graph app expression 1-1, so it got the A, and then I mapped it so that it created a list containing the AB, so it pushed it across.
Okay, so if I want to extract A off this, remember map always boils down to a list, correct? So if I take this list of two lists and I just grab this var expression. So let's look at something here. I'm gonna comment this out for right now. We're gonna go ahead and we're gonna say define val. Oop, that's not what I wanted. I want this. And then let's, oh, we're good there. Oh, it's complaining about up here. Just close that off for this moment. All right,
I
so.
think that's going to contain the word list inside of it because you put a quote beforehand.
Oh,
There we go.
okay. Let's just make sure this guy looks the way I expect it to look. Does that look about right? All right, so we're just going to operate on this little example here. So first thing I can do is if I say cooter of val, now I have that guy. The list containing in this case, 2 app expressions, right? I want to get a list containing only A and B. So the car of the catter of list ref 1, or list ref 1 gives me the A. Isn't that right? So if I say, quickly write a function here. So let's define, well, we'll just write it in here. So we're going to map a function across that list. The function we're going to map across there is lambda LST. So this is the list that we will get each time through, something that looks like that. And what we can do is we can go ahead and take list ref 1 of list ref 1 of that guy, and that should give us just the A. List ref 1 LST list ref 1 of that guy.
You gotta switch the one.
Oh, it's the LST first. Okay. Oop. So we're going to map this function, the function that across this list of lists. Each element that comes in this function is going to be a list, and what am I going to do? I'm going to extract list ref 1 of list ref 1 from that list. So in the end, this should give me the list containing just A and B, like that. That makes sense? Similarly, I can map this guy, where now I want, what did it look like? So I need list ref 2, list ref 1, right? So list ref 1 of list ref 2. Oh, wrong one. Well, I guess it didn't matter. And this should give me the list of values, 5 and 7. So those are the 2 things I want. Okay. So now we can come up here to our extend env for let. And we can go ahead and use extend env for lambda. Extend env for lambda, passing it my list of vars, which is going to be, let me actually kick this down a line. That's my list of vars. Passing it my list of vals. That's my list of vals. And passing it the current environment. Like that. Now that's extend env for let. So now, let's get rid of this extra junk here. Now we should be able to parse this. We should be able to run this. So it should create a local environment with 5 and 7 in the local environment. And then we should add those 2 together. Oh, it's not val in here. It's called app expression.
I was just about to say that. Like, you left something.
There's our 12. Well, where am I printing this dude out?
Yeah, all the way at the bottom. Parse expression.
Oh, thank you. All right, so is that the homework solution? Does that seem to solve what we were trying to do? All right, so we did leverage old stuff. Now, let me ask you this. So as a follow-up, so from a language design perspective, we may have been we may have thought we should put these into helper functions, right? What argument could you use not to put those into a helper function other than the fact that it seems awesome to build complex maps and stuff like that? Given our current interpreter, what's the advantage of these guys not being in a helper function? Or maybe if I flip that around, when is it a good idea? If you were to give me a rule of thumb when something should be a helper function, what would that be?
When you can reuse it for multiple things.
Reuse it for multiple things.
This is
Okay.
kind of one.
Aren't these guys pretty specific to this exact problem we're solving? Now, we certainly could do a helper function to try to keep ourselves sane rather than kind of embedding, because what gets scary here is where you're kind of building this inline lambda.
Becomes legacy code.
Well, potentially. But we have two side effects here. So first of all, we have an example of coupling, right? What's the example of coupling here? What two things in our interpreter, well, we have more than that, but specifically in this example, what two things in our interpreter is this extend env for let dependent on? Format for the input. Well, let's follow up. Who would be dependent on the correct input? I think this will take us down the path. Who cares that this input looks right? That guy, right? He's the first one that touches the input. So if our input's in any sort of bad format, parse exp isn't going to swallow it right. Okay? So parse exp relies on this guy being the correct input. So I think our entire interpreter is always, I don't think there's any way to decouple that, right? We always have to be reliant on the person using the program right. So now, go ahead.
Would I be able to do it if like your let expression was bigger, like too big? Would parse be able to swallow it?
Well, I think yes, but there's a point where if it's there's going to be a theoretical maximum for what's the largest list you could hold. So I don't know what that number is, but I don't know, maybe 2 billion things or something like that. 2 billion name value pairs if we do size of int or something like that. So short answer is yes, but nothing that we could fix. There's going to be a limitation to memory and stuff like that. Okay, so our entire interpreter is reliant on us giving it input that it can use, right? Parse exp does something with a let. It takes a let and it turns it into something else, right? Does that mean that the whole rest of the interpreter is reliant on the job that parse exp does? Because we've written the entire rest of the interpreter with parse exp's output in mind, haven't we? So we are making this assumption that lets will always get turned into these app expression clusters, right? So now we get back up here and we look at our extend env for let, this guy. That's why I wrote that variable name, to remind us that that guy is always going to be an app expression. Now, does he always have to be an app expression? Was there anything that we did that made it smart for it to be an app expression? Or was that just the convenient way for us to parse the let, given what we already had? Given the tools we already had, given the way we were handling our if expression from last time and things like that, turning a let expression into an app expression, parsing it into that, and just making sure that we can identify him as a let expression through that very first element, the car of it, allows us, I think it was the car of the cooter, because isn't the whole thing in an app expression? Whatever, but being able to identify that he's a let expression then allows us to say, okay, let expressions have kind of hijacked our app expressions format, even though we're not treating those guys as app expressions. That's what we did with these maps here, is we know that this guy is actually a this guy right here is actually going to be a name value pair where that's stored as an app expression. So we need to pull the pieces out of that. So this breaks if our parser decides to no longer represent let expressions as app expressions. So that's another example of coupling. Okay, so at some point, you have to make a decision and there becomes a chicken or the egg problem, right? This doesn't work if we don't do this one way. All right, so that's let.
What? I have a question.
Sure.
Wouldn't, like, are we expecting them to put in, if we had, like, different ways to name variables and var val pairs, so wouldn't we want to create the helper function?
Different ways to name, okay, give me an example.
Like, aren't we always naming variables in var val pairs?
Mm-hmm.
So why wouldn't we create the helper function to, because that's going to, whenever that gets parsed, it's going to be in an app expression, so don't you always want to get a list out of them? So wouldn't you want to get low var or get low val?
Can we necessarily say that there'll always be, I don't necessarily disagree with you, but can we guarantee that we're going to need this again?
I would say, yeah, I think so. The way that we're passing in that we've been passing in var and vals, we have to have, like, there isn't a place where we don't separate them out into the var val pairs and then keep going with it. Am I wrong?
Do we? But we do it differently for lambdas.
I thought we did it in almost the same way.
The second part would be pretty similar, but the list of vars is just a parameter list of the lambda. It's already in the right format.
Okay, yeah, never mind.
Yeah, so I mean, even though we're doing similar stuff, we're doing it in different ways, so that's not a generic function, I guess. Now, lambda, this guy, oh, he takes in those
We're
anyways.
essentially working backwards too, because we have it in the correct order, and then we build it in a list of variables and list of values, and then we parse it back into name value pairs when we put it back into the environment. So we're going from the correct format to different format back to the correct format.
Let's try to do something goofy here. So we'll say let A equal 5, let B equal that. And we're going to say plus A. Actually, let's back off here. So the body of this, let's go. Plus A. Can we create another let in here?
I think that's pretty parse.
Let C.
Why would you need to make another let in there, though?
I want to prove that we can have embedded environments. All right, so let is going to have a list and then a body. Okay. And this is a list of name value pairs. So we're going to have a C is equal to 3 in there. And then we're going to say minus BC. So that let expression will boil down to 7 minus 3, which is 4, plus 5, which is 9. So the B is used in a secondary environment, which gives us a more local variable C. So we have the environment that has A equals 5, B equals 7. And then we have a more local environment where C is equal to 3. We do the math where it's going to resolve C in the most local scope to be 3. It's going to resolve B in the next most local scope to be 7. It's going to do that math. So this local environment here is going to boil down to 4. And at that point in time, that environment is now gone. It's been burned. It's been when we get back to here after this guy's resolved, the environment no longer knows about C. That scope is now gone because we're back to our previous environment that just has A and B in it. All right. And what are we doing? We're saying A plus whatever this guy boiled down to. Now, where we're kind of going with this is what if we want to update the value of a variable? All right, but let's just see if this works first. So this should give us a 9. Okay, there's our 9. So we can do pretty legit stuff, right? All right, so now what would have been cool in here is to say something like C is equal to 3, B is equal to minus BC. And then let's do plus BC. One more. All right, so B is actually equal to the old B, this guy, 7, minus this guy, but we're going to see a break here, right? This is not going to work. What, things have already broken? What broke?
Nothing.
Brains?
I don't know.
My eyes from all the parentheses.
Oh, this is nothing. Okay, so what we intend to happen in this case is what? We have a local environment having 2 variables, A and B, 5 and 7. Then we create a more local environment. So, this is just a second scope that has another variable named C, and then a new version of B, a more local definition of B. This definition of B uses the old definition of B, which is a 7, and I'm subtracting from it C. The problem is that when we're building this, we don't know about C yet. So just to see this work, let's go ahead and just subtract from it 2. All right, so now we should get 7 minus 2 is 5. Now we're going to say 5 plus 3 is 8. And then 5 plus 8 is 13. Too large for list.
What am I saying? Something
The
about
index
with
is
it
too
breaking?
large for this.
Hold on, that had to be bad input.
Yeah, because it should be.
One moment.
Oh,
Oh, yeah, it's bad input. That guy. That guy. There we go. Now, where's my plus? All right, so that is my list of
Oh, because you're not evaluating. B.
yeah, do we not support math expressions in our it should work.
No, because you're not evaluating.
Oh, we're not
evaluating for B.
We
We're just taking it.
You're just taking it. So it's just a variable right there, or a letter. You're never evaluating it actually.
We're just taking the car of whatever's in there.
Yeah.
We're not taking.
Let's see. We have to upgrade our parser again.
No, I think we just have to evaluate.
Yeah, call it
The-
expression on it.
Well, inside of the eval expression for our let.
We have to check if there's a variable in there.
Well,
Let's just see what this is.
a lit expression, or it should be something else. We should just be able to evaluate it and have it boil down to something.
Yeah, we have our op expression.
But that's not the one I was talking about. He was saying that, and then
The B right there, what's that equal to though?
This B?
Yeah.
It should be equal to the B in the current environment.
What point, what point do we evaluate that?
Well, right. That's what I'm saying. Is that as we are extending an environment,
We're
if
not-
we get an op expression, we're not supporting op expressions yet.
We're just taking the.
We either take literals, we take lit expressions, or we take var expressions, or we take lambdas. And lambdas we choose not to evaluate. Is that correct?
I think if we just evaluate what you had highlighted, it should work for no matter what. Because either it's a lit expression or it's going to be an app expression.
Let's see, extend env for where do we decide how do we handle lambdas versus others? When we added the ability for our variable environment to store values that are lambdas that do not get did we do that in eval?
I mean, you just have to call eval expression on that section of it.
Right, but we did that all in one place already. Was it here?
But we're not in a lambda right there.
Yeah, we're in an no, correct. I just want to see how we handled it here. This is it. So if it was a lambda, just keep it. Otherwise, eval expression on it. So we're doing the same thing here where we need to go through and deal with the values of those guys. So we need to do something similar to what we did here, which actually then becomes scarier. Because what we'd want to do is we'd want to do that at the extend env for let level, this guy. So right here, we're creating our list of values. Well, it's not good enough to create that list of values now. We now need to map across that list of values because that list of values might look like, let's see, right now we're getting, what does this guy look like? When we get down to that B. Yeah, because right now we're just haphazardly grabbing the this is always going to look the same way. So that guy's fine. It's this guy where we're just getting a list of values. We're assuming those values are always hard-coded numbers. So we were just grabbing the, here, let me show you. I'm going to give myself a simpler define and exp to be a let. Then we can say plus a b here. We'll just go back to kind of what we had before. So a5 b7. That's the end of the list of parameters. That's the end of the let. That's the end of exp. So let's parse it. So we'll see a simpler exp thing here. So what we're doing right now is when we get our list of vars, that list of vals, that map is just grabbing the 5, grabbing the 7. But the reality is this guy might not just be a number. This guy could be an op expression or something like that. In fact, what we really need to do is we need to go through there and look at the car of that list ref 0 and find out what kind of animal this guy is. So we know whether or not we need to evaluate it or not. All right, so at that point, our extend env for let, this only works for literals as it stands right now. Right? Okay, we need him to work for more complex types than just literals, unless we only want it to work for literals, but that's going to be limiting. So when we get this map back, we've assumed that we're always dealing with the literal, when really we need to look at these values here. So let's get, this is list ref 0, 1, 2. All right, so this guy right here, just steal that map. Come down here. Paste that in. Let's grab all this. Well, actually, we don't even need to grab that. We'll just say define val to be equal to this guy. And we'll still print it, that way we see it. All right, so now that's val. And then we can say cdr of val there. So this should now give us a list containing all the values, not as literals assumptions, but as expressions, right? This should give us a list of expressions that are the values. So this guy looks like this.
You want to hide that first parse expression.
You're going into the lit expression, or the let expression.
Okay. Wait, hold on. Why is the program still running?
It's not. You're trying to define val and then you're mapping something to, because you're still technically parsing it now. It's just not printing it.
Right. All right. Let's look at val here. I just want to get the cdr of val. Go here. All right. So that's the cdr of val. Oh, we still haven't gotten the rest of it off. So we need to get the cdr of val, cddr, until we have the right piece. So now, oh, cdd, we want to get down to that app expression.
You want the car of those two cdrs? Is that what you want?
Let me go.
Well, don't you just want to evaluate the?
We need to get it back into the format that we're sending to our extend-env for lambda, or extend-env for let. So we don't need the app expression. We don't need this guy. What we really need is list ref 2. This is 0, this is 1, this is 2. That's what we want, is list ref 2. List ref val 2. And that should give us a list of our expressions. Oh, and then we know he's an app expression, so we can just peel off of that, right? So the cdr of that gives us the list of our dudes. Yeah, here we go. Okay, so that gives us this. But what we want to do for right now is let's go ahead and let's change this guy to be, I don't know, like a D. All right, so now we have something that's not a lit expression, just for our example. All right, so the idea would be that when this thing's being evaluated at some higher scope, we have our variable D defined, or this is bad code, one of the two, right? All right, so this guy would then turn into this. So as we are getting our list of variable names, the code we currently have up top would work just fine, right? Code we currently have up top will always, 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 always give us the correct list of variable names. Just grab that real quick. That's this guy. We'll just change app expression to val. So we don't need to worry about that. Let me just get rid of this. Let's put it there. Well, and of course I need to go back and recopy now. And we're going to let val equal this guy. Let's go get that line up here again. right here, copy. And then to change this to val. All right, so this should always get us the list of variables because those don't change. That's our B. Print out val here real quick, make sure I haven't done too much to it. All right, so list ref 1 of that guy. So we're mapping this function, list ref 1 of list ref 1, across, oh, just val, because I've fixed val now. I did a bunch of massaging to val up here, so val's now in the form that we want it. It was creepy, but I did it anyways. All right, so there it is. There's our map for our variable names. So we always get that. Now the issue we have though is now we need to get our map for our variable values, and sometimes those variable values aren't literals. They need to be evaluated, right? So that's where we need to have a secondary map. So this is where that secondary map comes from, and let's go ahead and change this to val. So let's look at this. This should give us a list of, this guy right here, our values.
So you can make it work quite easily by in your extend env for let for the when you're mapping the second lambda, instead of taking a list ref, you just eval that parameter and it should work. If you scroll up to your extend env for let. Yeah, that second map.
That's what we're working on down there right now.
Yeah, if you literally just replace the list ref and you just eval that, it works.
But it wouldn't for a lambda. The lambdas are not evaluable. It would almost work.
Yeah.
I mean, so that's equivalent to this down here of saying, so we get this line right here, ultimately, and here, let me just get rid of val here, just so it's cleaner. This is our line. This is a list containing our unevaluated values, right? Most of these guys can be evaluated, but specifically lambdas cannot be evaluated. So if we go through here, if it's a lit expression, we can evaluate it. If it's a var expression, we can evaluate it, so on and so forth. And each one's going to be evaluated inside of the current environment. But we need to treat lambdas as special cases. Lambdas are stored procedures that only make sense in the context of an app expression. That make sense? We can only evaluate a lambda if we have the input to send into it. And that only happens inside of an app expression. That was our homework assignment when we added the ability to store functions, store lambdas as name value pairs inside of our environment. So we need to go through and do something similar here where, I mean, for right now, if we want to make this, if we want to just be careful about our input, the simplest version of this would just be map eval expression across this guy, passing it our environment. That would be the simplest version of that, right? So if we want to just see this work, we can say map, we'll just say empty env is our sample environment. Actually, let's do this. Let's make it so that that var expression works. We have extend env, extend scope. Oh, we'll just do extend env for lambda. That'll be easy enough. Extend env for lambda, and we give this guy a list of vars, right? So we need to give it a D. and then a list of corresponding values.
You always have to give it the D.
List of corresponding values. And then the environment that we're extending looks like that. All right, so now we can evaluate this guy in that environment where we have a is 5, a B is equal to D, but we need to go ahead and evaluate D to be its value, which is actually a 4. Okay? So I'm going to map eval expression over this, the thing that looks like this. That's what gets returned by my inner map here. My inner map gives me this list. If I apply eval expression to that guy, given any environment, I get a 5. If I apply eval expression to this guy, given the extended environment I put over there, I just hijacked extend env for lambda, just passing it the stuff it needs to give me the a variable d is equal to 4. This guy should now boil down to 4. So now I should get a list containing 5 and 4 out of that guy. All lists must have the same size. Oh, yeah, because of the environment. Gotcha. So we're not mapping eval onto that guy. Remember, this is our little trick. We're mapping a lambda that takes in an expression, and what we're doing is we're calling eval expression on the expression in the environment that I extended. Okay, I need one more guy here. So there's the lambda. So I'm mapping that lambda across that list. There's my list 5 and 4. So this is what I actually want to do up there.
That's just for the value, right?
Extend the just for the second part, this guy here. And it's not val, it's app expression. Like this. And also, we don't need to give it an extended environment here. We just give it the environment we have. The one that was passed into us right here. All right. So now I should be able to let's see. I guess to really test this, I'd want to do this. Let's get rid of this guy. Let's get rid of this guy. And here's our expression, but we want to make our expression a little bit more complex now, because now we have this.
There's one to run above it.
Huh?
I mean, if you think it'll work, might as well go for the big one. Go bigger, go.
This will work. C will work. That should work. What won't work is we won't be able to we won't be able to say B is equal to B minus C, because we don't know about C at that level. That's what a let, that's the difference between a let and a let star, which is where we're going with this whole thing.
Yeah, run program.
Oh.
Uncommon. Like that. Extract, expire, first
follow through this. So this is I get an environment A, B is 7. And what am I doing in the body of that guy? I'm doing that stuff. That's the body of the let. And in that body, I'm adding A, which should resolve to 5, into the let that now has this body. C is 3, or this environment rather. C is 3, B is going to be equal to the result of the old B minus 2. Yep. That's the end of that guy. So then we say plus BC, so this should be the new more local B, which should be 5, plus C, which is 3, so this should boil down to 8. So that guy is now so that boils down to 8. This then boils down to 13.
So is what you did up there supposed to work for lambdas too?
It won't work for lambdas yet. So I'm not going to give it lambdas.
Oh, well, why don't you just?
Well, we're going to make it work for lambdas.
Okay, I was like, you're doing
We
way
have-
too much.
we
for
have
it
to
not work
we
for
have to
lambdas.
treat lambdas as special cases.
Okay. Because
Yeah, because we want to support doing something like this, where B can be a lambda x plus x2, something like that. We want to support that.
Sure.
That should eventually work, but we can't evaluate this. We just want to store it as is in the environment with the B. All right, so let's see.
Because to get that working, you're doing a lot of extra.
Well, not really. I mean, mapping it across there shouldn't be a real problem. My concern here is what do these environments look like? Let's
You only have to really do one map if you want to.
let's look at this guy here. And here's that second. Is this where I'm dying on this guy?
Why are you?
I'm extending that environment. All right, so I really want to just see what that looks like, what that environment looks like. Let's see if we can get to that point. So let's go up here. This is for our let. We're no longer going to actually evaluate that expression. We're just going to do this. One more closing. There we go. So let's just see what that environment looks like, what it thinks that environment should look like. Okay, so that's where it's dying in that.
Is it dying in the parser?
Oh, okay, good. 25, we do.
Oh, what's D?
Oh, all right, well, this is good. So something that was working is breaking. So I'm guessing, do we have a val somewhere that should be a?
Well, were you working with the parsed?
Yeah, it's right here.
Before?
I think we might be making an assumption what that guy looks like. When our app expression comes in there, remember I said I massaged it down below? And maybe haven't massaged it enough here. Okay.
Did you use those words before?
I think I did. Oh, the down below thing, phrasing. I get it.
Yeah.
Now you're really gonna have
I didn't hear it when it came out, but I hear it now.
I think you have a strong chance for Cialis ads
Is-
after glasses.
Oh man. Oh, it's pretty funny. All right.
Well, who knows? There might be some like old computer science, older computer science guys in career, like watching your videos for review. It might apply.
You might be right. I suppose you could be. All right. So
Oh, you're not taking the cooter of app expression.
I just did that. Oh! I was taking the cooter of that guy. Yeah. I actually need to massage it over here. keeping
Massage it up top.
with our creepy theme. So I over massaged down over there.
Up a little bit.
All right.
A little more to the right.
Let's go back here. Okay, there's the environment. B is 7, A is 5.
So you can put the actual code back in.
But we should get a second environment from this guy that has a C and a B.
Well, no, because you're evaluating them out.
You haven't gotten the evaluate
You've
yet.
already taken them and did what
Oh, because I didn't call eval expression on those. I get it. All right, so that means I should be able to, let's do this, then this. Yeah, there's a 13. All right. All right, so this guy now works for something that looks like this, where you have a let inside of a let, and our local one is implemented in terms of a our inner let is implemented in terms of a variable in our outer let. But what we don't support right now is something like this. Let me just steal this whole line. Comment that out. Go here. A5, B7, C3 minus C. Okay, let's say times C2. That's what doesn't work currently. All right, so this guy allows us to have, well, we'd like something like this to work, right? That is, within an environment, if I define C is equal to 3 first, I should then be able to define B in terms of C. That would be something that would be nice to be able to do. Okay, our let does not support that. Now, what's interesting is in Scheme, we have let stars and another guy called a let rec. Well, what we're seeing right now is the limit of let and what let stars do that lets do not. Let stars allow us to define variables in terms of themselves here. Okay, so what we need to do for our homework is fix let so that it would work for this guy. So the output for this guy should be what? So C is 3, B should be 6, B plus, so 6 plus 3 is 9. So this guy boils down to 9 here. 9 plus 5 is 14. So this should boil down to 14 in this case.
You can't even do that math by hand.
All right, so here at the end, let's just do should be 14 when working. Okay, which is also kind of a phrasing, but in a less creepy way. Unless you make it creepy.
And we all did.
All right.
Depends
So
where she's working.
let's go ahead and let's get this pushed up to GitHub. History grep for CD. pound 692, or bang 692 rather. All right, and then we want to, actually was this, that's 2013, that's not the one we were doing. We made a new one, right? Where's 2015?
694.
6642. There's Amish. And then we're going to have get add star, whatever, get commit dash m, let works, but let star abilities do not. And then history, grep or push, bang 713. Let's make sure it's up there. Huh?
What's the grep do?
Shows you.
Oh, grep allows me, it when I say history, it shows me all the stuff in history. When I pipe the output of that to grep, it allows me to like search it for stuff. So I can search for anything that has push in it, which gives me just the push stuff.
I don't want to do that on my computer.
Why? Let's see, that's not the... Oh, here's repositories. Amish programming language. Okay, 36 seconds ago. So I'll go ahead and put this up for the assignment. So the assignment is update the let to support let star stuff. That is, you should be able to use a variable previously defined within the same let scope to define a future variable in the same let scope. So the easiest way to say it is make it work like let star. Now you just have to know how let star works.